Okay, so today we talked yesterday about limits that approached infinity or approach negative infinity. We're going to kind of talk about that a little bit more today with an end behavior model for rational functions. Right? If you remember back in pre-calc, you probably had like a table where for the horizontal asymptote or the end behavior asymptote of a rational function, you compared the degrees of the top and bottom, and if the top degree was bigger, there was no horizontal, and if they were equal degrees, it was like some line. If the bottom degree was bigger, it was just y equals 0 was the line. So we had all that. Well, with limits, we could kind of look at it differently. And actually, what happens is, for any rational function we have, right, if we want to find the end behavior model, now this tells us what's going to happen at the ends of the function as we approach infinity and negative infinity. And we'll get a graphing calculator out here and look at this too, because I think it's a little bit enlightening here. Or maybe I'll let you do it. But with this, all we have to do for the end behavior model on any rational function, as long as a, x to the n, and b, x to the m, are the leading coefficients of the numerator and denominator, right, the biggest powers, you just take a divided by b to get a constant, and then just take the top degree minus the bottom degree. And that's it. So if they're the same degree, you'll just get a over b like we saw back in pre-calc. Right? But otherwise, we'll get other functions as well. We could have a bunch of different things happening here. So, because what's happening is we approach infinity, like for example 1 here, if you take a really large number and square it, it really dwarfs the really large number itself. Right? Or if you take the bigger the power, just the more impact it has, the bigger the number gets. So what happens is this basically our end behavior model for this would be y equals 7/3, and then we have a squared on top and a squared on bottom. So it's just going to be y equals 7/3. That's all we're going to get there. We'll look at that in a second here. So for this next one here, the end behavior model, we have the same kind of setup, correct? So with this one, we'll get for our end behavior model, y equals, you'll get 2/7 x to the 2 minus 3 power, which is y equals 2/7 x to the negative 1 power, right? Which is a hyperbola, right? So we'll get that kind of shape there. It's 2 over 7x, if you want to think of it that way. And then we'll need to look at some calculator. So if you're watching the video, I would recommend you go ahead and graph this function, and then graph this function, zoom out, and they should look the same on the ends. Okay, same thing here. Graph this function, zoom way out. They should look the same on either end. We'll do that in person here. And then for this one, the end behavior model, is going to be y equals 2 over 1 and then x to the 3 minus 1. So y equals 2x squared would be the end behavior model for that one. So with that, we could go ahead and take a look at those. And actually, okay, on our example 2 here, I made a mistake. This is not the correct function. It is the formula though, right? It is the formula, but this is an end behavior model. The end behavior occurs as we're approaching infinity and negative infinity, right? So if you take, again, this would be the same as 2 over 7x, right? Because that's what a negative exponent means. And if you think of that, as we approach infinity, you're doing 2 divided by an infinitely large number. So what's it going to approach? It's going to approach 0, right? Just like we would expect. So this limit would be 0. Right? Does that make sense there? Because we can't, if you take 2 and divide by a giant number, it's going to approach 0. That's kind of how things happen. Yes?
So if the numerator is smaller than the denominator, is it always going to be 0?
It'll always be 0. Just like the rules you learned in pre-calc. Yeah, you guys, I made a mistake there, but that's exactly what it is. Are we good? with that? Now, what is interesting though, is we do want to maybe graph this one on your calculator, this function, okay? Go ahead and graph this function, and then also on the same screen, we're going to graph this function here, this 2x squared. So go ahead and graph this, what we're taking the limit of, to find the end behavior model, and then we'll go ahead and graph the y equals there also. So again, we're going to do that 2x cubed plus 4x plus 1. That's 2x cubed.
Wait, can I see your equation? I don't know.
How do you change the window on Desmos? You guys know about this thing?
You just scroll out.
But how do you like, what if I just want to change the y's and not the x's?
You can't do that.
What?
There's probably like a cookie you just grab.
What do I do?
I didn't know that.
You're gonna learn me some
Why do you
Desmos?
guys have that here?
Yeah.
Why does hers not? I Okay. Why am I getting another line? What the
I saw that.
Let me see your
I thought you might be in it.
Wait, Sarah, let me see your equation.
What though? Wait,
She's just doing US squares. Yeah, I
Very
think that's.
nice.
That's what mine looks like. I literally have the same exact equations. Look.
A lot of legs.
Are you somehow?
Yeah,
like,
yeah.
Are you in mode?
I did. Did you get like?
I have no idea. I think you just put in rate mode.
Yeah, like
I am
curve,
radiant.
like that, right?
Yeah, that's weird.
All right, I guess it's gonna be hard for me to talk about.
What does
but-
your graph look like? I love
All right, so if we graph this first function, it's just a weird function, correct? And I was back there trying to type on my wireless keyboard to make that computer work, but up here apparently I Googled something random for Microsoft because it's the wrong computer.
I don't even do it.
Ours is the same.
Yours is?
Well, I did do it, but mine was like this.
Oh, I did.
You gotta do parentheses around the top and the bottom.
I did too. Oh wait, did not do.
Well, that isn't what I wanted to have.
Wait, when?
I need a technology coordinator.
2x.
How did you do?
Oh, I got it. No.
Oh yeah, I got that.
Oh, yeah.
Okay, like when I asked you to, can you click there, show the other one? Will you be like my computer coordinator? I do have a technology coordinator. All right, are we ready? This has not been done before in terms of my technology stuff. Yes?
When I plug the first equation into my calculator, it does like two different lines.
Like this?
No, like it does like, whooshoo. No, like, whoop.
Let me look. I don't know.
Yours does the parabola and then another one.
Yeah.
How did you get that? Cause like,
Yeah, well, you tried.
well, I know I have to.
You had 2 functions.
Why does his like, why does, when
No,
I
I'm
put in
trying.
2x squared.
Because you're not zooming,
Yeah.
he's zooming out.
There's 2 keys.
I know, but his parabola
Yeah.
doesn't even cross the y-axis.
No,
but okay. That's what it looks like.
It's supposed to
That
be
2x
both
squared?
sides?
It's supposed to be. kind
Yeah.
of-
It's not even on his graph.
Oh,
No,
thanks.
like,
Thank
you
you.
look, you look, you zoom out, it's the.
Well, I don't have that like little.
Yeah.
You're like, can I see
No,
your
it's because
equations?
you're not like.
Okay, so, Sia, can you zoom us back into about a 10 by 10 window? Can you do that? See, that's awesome. That's a pretty good one. That's great right there. That's great right there. Thank you. All right. Any questions there? Thank you, Sia. That was awesome. I mean, I don't know, it was probably pretty lame, but it was awesome for me because I didn't have to run back and forth the whole time. Does that make sense on the end behavior model? It's kind of underwhelming mathematically, right? You just take the top power minus the bottom power, leading coefficient, there's your end behavior model. But it's nice to know that even if you get a really crazy looking function, that you can do that and it'll show you what's going out on the ends of the function. So it's a powered up version of what we saw back in pre-calc, right? Where you got horizontals. Did you ever talk about slant asymptotes? I mean, you will, like if the top degree is 1 bigger, your end behavior asymptote will just be a diagonal line. But here, this is like a parabolic end behavior asymptote, right? Because it looked like a parabola, right? It approximates the shape of the parabola as we went out. All right. Now, what I want you guys to do is, I think, let's see how we do with this. For this picture, okay, you might copy it down. We'll talk a little bit about it. But for this, I think that looking at this, you can tell where it's not continuous, right? I hope, right? We know the definition. We know what continuous. We have an idea of looking at what it means to be continuous. Is that true? Okay. Let's look at what's going on with the limits at those points, and let's investigate the limits at the points where you think it's going to be discontinuous, and see if we can kind of find some pattern there. Okay? So just take a few minutes, kind of look at that. So we, probably -2, 4, and 8 are probably good places to start. But try to think about, like, do you guys think it's continuous here? No. Let's investigate the limits and investigate the values of the function and see if we can find some definition of what it means to be continuous. Just take 5-10 minutes, just kind of goof around with it. Okay, then we'll come back and we'll kind of wrap it up and look at what it really means to be continuous.